Hey everybody, today's lesson is going to be about inequalities, and it's going to be a little different because you're going to see me in front of the whiteboard. I didn't find any videos that I particularly liked, so I'm going to go ahead and teach this one directly, okay? And so inequalities, think about the word unequal, right? That means we're not going to have an equal sign in our problem. So, for example, I'm just going to show you where we're going to get to with this. Before, we were doing problems that maybe looked like this. 3 plus x equals 5, right? An equal sign. But now that we have inequalities, they're going to look like this. 3 plus x is perhaps greater than 5. Okay, so instead of an equal sign, we're going to have a different kind of symbol, a greater than, less than, or greater than or equal to or less than or equal to symbol. And we're going to go over those symbols, and so you can get familiar and comfortable with those before we get into some of the harder problems that deal with algebra. Okay. As always, feel free to pause the video, rewind, right, and watch things again to make sure that you had a chance to do it. Or get it copied into your notebook. All right, so let's start with the symbols. So our symbols look like this. There's one that goes like that, one that goes like this, and then a couple that go like that. Okay? So these are our different symbols, and I'm going to break them up a little bit so you can make sure that you tell the difference between them. 1, 2, 3, and 4 there at the bottom. Okay? And so what do these symbols mean? Okay? Typically, we think of this sign as the greater than symbol. I'm going to fix my computer really quick. Sorry about that. So this one we call greater than. Okay, that's the greater than symbol. This one is the less than symbol. This one, because it has this line underneath it, you notice that, means greater than or equal to. Greater than or equal to. And this one right here means, you guessed it, less than or equal to. And we always know if it can be equal to if it has this little line underneath it, like half of an equal sign, sort of, right? Okay? So that's what those symbols mean. And you can see them in different ways, right? You might see, and I'm going to write them over here, x is greater than 3, which tells us something about x. It's a number that's bigger than 3, right? Just helps us figure that out. It could just be with regular old numbers, right? 3 is less than 5. It could be x is greater than or equal to 4. Or x is less than or equal to -7. Okay? So these are the different ways that we'll see it. And one of the main things that's different with inequalities is often in a math problem, they're going to ask you to graph an inequality on a number line. And so we're going to need to specify between whether something is greater than or equal to or greater than or less than when we do that. But before we get into that, let's just give you an example of what a graph looks like. Okay? So go ahead and pause. If you don't have this down, I'm going to erase it. Let's look at our first one. X is greater than 3. Okay? So we have a number line, right? Let's say that this is 0, this is 1, this is 2, and that is 3. Okay? So how do I graph x is greater than 3? Well, with the greater than or less than symbol, when we graph it, to show that it's not equal to 3, we use an open dot on our graph. like that. It's not a 0, it's an open dot, okay? And so when we graph it, that's how we know if it's greater than or less than. So x is greater than 3. So that means that it's not equal to 3. It's bigger than 3, right? So how do I show that? I put an open dot on my 3, okay? And that shows it's not equal to 3. And which way is greater than 3? This way, right? I'm off the screen. This way. And it goes like that. And I show an arrow to show that it goes on forever. X can be any number bigger than 3, but it's not equal to 3, right? And that's why I have an open dot, okay? Let's show you another example on a number line that's a little bit different. This time we'll say x is less than or equal to, let's pick another number, 1. X is less than or equal to 1. Less than 1, okay? Here is 0 and 1. We'll call this negative 1, okay? So how do I graph this one? Well, when I graph something that's less than or equal to, I have to use a closed dot, like that. That specifies that it can also be equal to the number in our inequality, okay? So I find 1, and now I'm going to use a closed dot because it's a less than or equal to symbol, okay? Which way is less than 1? Well, isn't it that way, right? And so that means my graph is going to show going this way and go on forever with my arrow, okay? So this shows x is less than or equal to 1. Here's 1, closed dot to show it can be equal to 1. X can be 1 or any number smaller, okay? That is the basics of graphing inequalities, all right? Why don't we do one more example together, and then you'll have to answer a couple on your own, okay? So here's our third example. I'm going to call this one x is greater than negative 3, okay? So here's my number line. Here's 0, negative 1, negative 2, negative 3, right? And 1 over there, for example. Okay. How do I graph x is greater than negative 3? Okay. Well, I got to find negative 3 on my number line, and here it is right there, right? And since it is a greater than symbol, I have to use an open dot on my graph, right? An open dot shows that it's not equal to 3, right? It's not x is greater than or equal to 3. It's just x is greater than. So I use an open dot, okay? Which way is greater than 3? It's going to be this way, right? Getting more towards positive is greater. It's a greater number. So my arrow goes this way. And this shows that x can be any number greater than 3, but not equal because of that open dot, right? So you're going to answer a couple questions in a row now on your Edpuzzle video. Okay, hopefully you got those questions right. If not, maybe you should go back and re-watch just so you hear it again, right? And get some extra practice. All right. So now let's talk about another way that we use inequalities. Another way that we use inequalities is in algebra, okay? For example, x plus 2 is greater than or equal to 5, okay? Imagine that this is just an equal sign. How would we solve this problem if it looked like one that we're used to? All we would do, you're right, is subtract 2 from both sides, right? Subtract 2, and we'd say x is equal to 3, right? This is the same exact thing, except we don't have an equal sign, we have an inequality symbol. We're going to do the same steps. You can put your dotted line down your inequality. Whatever you do to one side, you have to do to the other. In order to get rid of this positive 2 and get x all by itself, right? That's our goal, is to get x all by itself. We're going to subtract 2 from both sides. We're going to do the opposite operation to get rid of 2, right? Subtract 2, subtract 2. X is greater than or equal to 3, right? Now, graph your answer, right? Here's 3, 2, 4, right? Greater than or equal to means I have to use a closed dot. Which way is greater than? It's going this way. Notice how my graph usually follows the tip of my symbol. See how the symbol's going that way? And so is my graph. That often happens, but not always. So it can help you sometimes, but sometimes it might trick you. So just pay close attention. But in this case, it follows the way that the arrow's going, right? So that was one basic algebra problem. Let's do another one. What if we had 18 is less than 9x, right? So let's think about what can x be? What can x be? Well, I have to figure out what x is, right? Here we go. Dotted line down my equal sign, or my unequal sign, I should say, right? And now what do I do here? This is 9 times x, so in order to get x all by itself, I have to divide both sides by 9, do the opposite operation. That cancels, divide this side by 9. 18 divided by 9 is 2, you got it. Bring down my symbol. Now I have 2 is less than x. Weird, it's kind of written backwards, right? It might be hard for me to graph because x isn't first. Why don't I just make x first? How do I do that? Well, let me look closely, and I'll see that the mouth is eating the x. Imagine there's some teeth there. It's an alligator, right? It's eating the x, right? So I'm just going to peel this back. I'm going to peel it back and write it the other way, right? So I'm going to say x is first, and my mouth has to eat the x, right? And then 2 goes over here. So 2 is less than x is the same as x is greater than 2, right? Now I could graph that. Here's my line. Let's call that 2. What goes here on 2? An open dot, right? Because it's not equal to. My open dot, which way is greater? Which way is the arrow going? That way, right? This way is greater, and now I have it graphed. Awesome. Let's talk about one more thing with inequalities, and this is going to be the trickiest thing. And guess what? It's going to involve integers. Our favorite thing, right? Everyone's like, Jeff, why did you start the class with integers? My brain hurts. All right. So let's take a look. This I'm going to just start off by going over something to help you try to understand it. Think about algebra. Let me give you a true statement. This is a true math statement right here, right? 4 is greater than 2. That's true, right? Nobody's going to tell me that 2 is less than, or 2 is greater than 4, right? 4 is greater than 2. We can all agree. In algebra, we have the rule that whatever you do to one side, you can do to the other. And it keeps the statement balanced, or it keeps it true, right? So let's see what happens if I do something to both sides. Will it stay true? Let's add 4 to both sides. Will it stay true? 4 plus 4 is 8. Keep my symbol. 2 plus 4 is 6. Is 8 greater than 6? Yes. It's still true, right? Still true. Let me rewind here. Okay. What if I do something different like divide or multiply? Let's divide both sides by 2. Divide by 2. Divide by 2. 4 divided by 2 is 2. Keep my symbol. 2 divided by 2 is 1. Is 2 greater than 1? Yeah, that's still true, right? So my rules of algebra are still applying to inequalities. Whatever I do to one side, I do to the other, and it stays true. Let's look at a couple more examples. What if instead of dividing by a positive number, I divide by a negative number? Or maybe multiply. Let's try that. So what if I multiply this by -1? We'll just keep it simple, right? If I multiply this side by -1, I have to multiply this side by -1, right? Okay, let's see what our answer is. Remember, when we have integers and we multiply or divide, a positive and a negative make a negative. This is for multiplying and dividing, right? So a positive and a negative, different signs, make a negative answer. So that's -4. 2 times -1 would be -2. So now our statement says -4 is greater than -2. I hope your mind is telling you, wait a second, that is a false statement. -4 is not greater than -2. It's a bigger digit, but it's not a greater number. Think about a number line, right? Here's 0, -1, -2 is one of ours, -3, -4, right? Which one's greater? It's -2, right? That would be a greater temperature, right? -2 than -4. If it's closer to 0, it's a bigger number. So this is a false statement. -4 is not greater than -2. So what does that tell us about inequalities and when we do algebra? Here's what it tells us. If we multiply or divide by a negative number, we have to flip the sign to keep the statement true. So instead of keeping the sign the same, when I multiply or divide by a negative, I have to flip the sign the opposite way. That changes my statement from false back to true. -4 is less than -2. That is a true statement. So we have to keep in mind when we do inequalities that whenever we multiply or divide by a negative number to both sides, that sign is going to flip over, right? Let's do an example with algebra. So let's say we have -3x is greater than or equal to 12. Remember, we're just going to solve it like we would a normal algebra problem. We'll put our dotted line down the equal sign or the unequal sign. To get x by itself, I have to do the opposite. Here we're multiplying. Now I'm going to divide by -3. If I divide this side by -3, I have to divide this side by -3. Notice I have an inequality and I'm dividing by a negative. According to what we just learned, whenever we multiply or divide by a negative on both sides of an inequality, we have to flip the sign to keep the statement true, right? So I'm going to flip the sign. First thing, I'm going to flip that sign over. As soon as I say I have to divide both sides by a negative, I'm going to show that I flipped that sign, right? I flipped it. Then I'm going to do my math, okay? -3 divided by -3, those are going to cancel each other out and just leave me with x, which is what I want, right? X by itself. 12 divided by -3. We're dividing, and our signs are different. When our signs are different and we're dividing, that gives us a negative number. Okay? 12 divided by 3 is 4. So my answer is x is less than or equal to -4. Okay? I could graph that on a number line. If this was -4, this would be -3. This would be -5. Zeros over here, right? How do I show x is less than or equal to -4? Well, it's less than or equal to, so I got to use a closed dot, right? Closed dot. Which way is less than -4? Not towards 0, right? Away from 0, so my graph is going to go this way. And that's how you solve an inequality when there's a negative in it. Okay? We'll do one more example, and then that'll be our lesson up for today on inequalities. Let's do a two-step problem. We'll call it n over -4 minus 4 equals negative, let's just call it positive 16. We don't want equals. What am I talking about? Greater than or equal to. Sorry about that. All right, two-step equation now. Remember when we do a two-step equation, we're undoing it, so we're doing order of operations in reverse. PEMDAS, right, in reverse. So that means we're going to start with addition and subtraction when we do a two-step equation. So we're going to leave the division alone for now and focus on the addition and subtraction. When we add, whoops, I dropped my cap. When we add or we subtract both sides of the inequality, we don't have to flip the sign, right? We learned that. We add 4 to both sides to get rid of 4, right? Adding 4 to both sides doesn't change my inequality sign. 16 plus 4 is 20. This one canceled, leaving me with n over a -4, right? Now for my next step, I have division, right? And so in order to get rid of this -4 that's on the bottom, I have to multiply by a -4 on the top. If I multiply by -4 on this side, I got to multiply by -4 on this side, right? I'm multiplying both sides by a negative. Remember, if I multiply or divide both sides by a negative for an inequality problem, that means I have got to flip my sign over. So it goes from this to this, right? Do that first thing so you don't forget, because it's easy to forget. These two -4s cancel out. 20 times -4, if I do the math, that's going to give me -80. Okay? And now I'm just left with n. So I know that n has to be less than or equal to -80, right? Of course, I could graph that. Don't start at 0. Just start at -80 if you're doing it on your own. There's -79. -81 is smaller. What kind of a dot am I going to use? N is less than or equal to, right? So I'm going to use a closed dot. Less than or equal to. Which way is less than 80? -80? This way. Right? Okay. So you'll have a couple practice problems, right? And we're going to, of course, work more on this in class and get you more comfortable. I know, again, this is not the easiest thing. It's probably something you haven't done in a long time or maybe ever. And so just be patient with yourself. Maybe watch the video again if you want to see more examples and get more comfortable. And we'll do some extra practice in class. Thanks for watching. Bye.